Welcome everyone. In this session, we are going to see various advanced neural networks under the subject neural networks and its applications. So, introduction to the radial basis function network. A radial basis function network, we can call this as RBFN, is a type of artificial neural networks that uses the radial basis function as the activation function. It is commonly used for function approximation, basic classifications, and pattern recognition. RBFN are feed-forward networks that maps inputs to the outputs using a localized distance between the activation function, so which makes them highly efficient for certain types of learning tasks. So the network which uses the radial basis function as an activation function is called as radial basis function network. They provide the localized responses, meaning each neuron is responsible for a specific region in the input space. They typically use the Gaussian function as the radial basis function. So in this network, we'll be using the Gaussian function as the activation function. So in RBFN, the training is usually faster when compared to the other neural networks like multilayer perceptrons. So this is the architecture of the radial basis function. So input layer, hidden layer, and output layer is used. And this function is nothing but the Gaussian function, which will be used as the activation function for the networks. Architecture of the radial basis function network. So the architecture will include the input layer, hidden layer, and the output layers. So the input layer is this layer consists of n number of neurons, where n is the number of the input features. It does not apply any transformation. The input layer will simply passes the input values to the hidden layers. So in the hidden layer, so this layer will contains all the radial basis function neurons. So in the hidden layer, each neuron computes the distance between the input and a center. So the center represents a prototype vector. So the activation function used is a Gaussian function. So the Gaussian function can be represented as e power minus beta into the r square, where r is nothing but the Euclidean distance between the input and the neuron centers, and beta is the inverse variance, which determines the width or a spread of the activation function. So in this network, the Gaussian function will play a major role, which acts as the activation function, and we need to calculate the neurons centers and what is the distance between the input and the neuron centers, which is represented as r, has to be calculated, and then the spread, which represents the width of the activation function. So the width, that is the spread also we need to calculate. So the hidden layer will transform the input into a high dimensional space, which will enable the better separation of the data points. Third one is the output layer. So the output layer performs a linear combination of the hidden layer activation. So if the network is used for classification, a softmax function may be applied to the outputs. So the overall function of the radial basis function can be expressed in this equation, where x represents the input vector, ci represents the center of the ith radial basis function. So W represents the output weights, and this phi represents the radial basis function, that is the Gaussian function, where the phi can be provided in this equation. So what is the training process of the radial basis function? The training and the radial basis function involves mainly these three steps. So the step one is selecting the centers. So apart from using the radial basis function as the activation function, the way we are training the radial basis function network will plays a major role. So this will include these three steps. So step one is selecting the centers or unsupervised and learning. So we need to select the neuron center. So the centers of the radial basis function must be chosen approximately. So the centers can be selected by using any of these three ways, like a random selection. selecting the random training samples as the centers. K means clustering. So K means clustering algorithms will be using an unsupervised algorithm to find the cluster centroids. And next one is the SOM, self-organizing map, the neural networks that automatically find the best centers. So there are multiple ways available to select the neurons centers. So the next one is determining the spread of the radial basis function. So the spread of each radial basis function determines how much influence each neuron has. So a small spread makes the neurons highly sensitive to the input changes, which leads to the overfitting. A large spread resulting in the underfitting. So if the spread value is small, it leads to the overfitting. If the spread value is large, which will result in the underfitting, where the network generalizes too much. So the spread is often set using a fixed heuristic value, the mean distance between the centers, cross-validation to find an optimal values. So the next step is computing the output rates by using the supervised learning. So once the centers and the spread values are calculated and fixed, the output layer weights are determined. The weights can be learned using the linear regression, gradient descent, or least square estimation. So in least square method, we represent the activation of the hidden layer as a matrix phi and the target output as weight. Then the weight W can be computed by these expressions. So this allows for a faster training in one step, unlike backpropagation in the MLP. So that's why the radial basis function, the training process is faster when compared with the multi-layer perceptrons. So these three are the main steps involved in the radial basis function. First one is calculating the centroid, neuron center value. The next one is the computation of the spread function. Then after calculating both, we need to compute the output weight by using the supervised learning methods. So the weights can be learned either using the linear regression, gradient descent, or least square estimation. So by adapting these steps, we can make this particular new network for faster training. So comparison of the radial basis function and the multi-layer perceptron. So these are some of the features and radial basis function networks and multi-layer perceptron. For the activation function, the radial basis function will be used, or the Gaussian function will be used as the activation function in the radial basis function networks. For multi-layer perceptron, sigmoid radio or tan H will be used as the activation function in MLPs. Learning approaches for RBF network, hybrid, that is unsupervised plus supervised learning will be used, whereas for MLP, fully supervised is used. For a training speed, RBF is a faster, multi-layer perceptron is slower. Approximation type for RBF is a localized response, whereas for MLP, we obtain the distributed representation. For generalization, for RBF network, it is strong for small data sets, whereas the multi-layer perceptron requires more training data. The RBF network is best suited for the classification function approximation, and for complex representation, we can go for the multi-layer perceptrons. So the radial basis function networks are faster to train due to the closed form solutions in the output layer. So they are less powerful than the multi-layer perceptron for deep learning tasks, but it works well in the function approximation. So the multi-layer perceptron requires backpropagation, making the training slower but better for the complex problems. So what are the advantages of the radial basis function? So the radial basis functions is a fast training method since the output weights are determined in a single step, whereas for multi-layer perceptron, it updates the weight by using the back propagation algorithm where that will be a time consuming. The next one is a good generalization. Radial basis function work will even with the limited data, making them useful for real world application. Then localized and learning will be used an interpretable model. That is the role of radial basis function neuron is clear and localized, making it easier to analyze compared to the deep neural networks and robust to noisy data. What are the application of the radial basis function? So radial basis function networks are used for the pattern recognition, function approximation, time series forecasting, control systems, and for medical diagnosis. So the conclusion is the radial basis function network are the powerful tools for function approximation and their classification. So they provide the faster training since we can obtain the output in a single step. So it provides a faster training, localized responses, and it is more robust to noise. While they may not be flexible as a deep learning networks, but they are efficient and interpretable, making them valuable for many real-world applications. So these are the architecture advantages, conclusion, and the training models of radial basis function networks. Thank you all.